All right. We looked at Boyle's law, pressure and volume, Charles' law, volume and temperature, Gay-Lussac's law with our pressure and temperature, and now we're going to put all three together. And it's called the combined gas law. P, V, and T, all three of them equal a constant. But in this case, I can change two of them and not just one. I can change two of them and then go look and see how the third variable is affected. The graph will always have this kind of shape, but at different temperatures, the whole graph gets shifted. We call these isotherms. So all along this basically pressure volume mark, we have the same temperature. Iso means same. So anytime you see iso in front of something else, therm is for temperature, as in thermal, it means it has the same temperature. So this is what we have that's constant. And just like in the previous one, since we have temperature, we're going to still have to be the Celsius plus 273 to get our Kelvin temperature. The thing is, we can change more than one thing, and so it's not so easy all the time to see how the final answer is going to get played out. So, we have a balloon filled with gas. It has 30 liters. What would that be? Volume. So, let's call that our V1, 312 K. Our temperature, T1, and we have a pressure, P1, of 162.1 kPa. All right, and then it says what would be the volume, so that's going to be a V2. At standard temperature or pressure, STP. Now, the only way this works is I have to have 5 numbers, and I solve for the 6th one. I got 6 things all together, so I have to have 5 of them. And you might say, well, I only got 3 numbers. STP, however, is 2 numbers. STP, what is the standard temperature? The standard temperature is 0 degrees Celsius. The standard pressure is 1 atmosphere. Okay, that's what STP is. However, this problem, well, we always got to change the temperature into Kelvin. So I'm not going to use Celsius, not to mention dividing by 0 would not work. That has to be changed into, add my 273, and so my temperature here will be 273 K. And if you remember from our conversion sheet, 1 atmosphere is equal to 101.325 kPa. Don't have to really do much in the way of conversions because it's 1 atmosphere. If it was 2.3 atmospheres, then I would have to figure out how many kPa that was. But since it's just 1, I can go right to it. So this then becomes my T2, and this becomes my P2. So I really do have 5 numbers, even though they weren't actually written in the problem. So, write down my equation, P1 V1 over T1, P2 V2 over T2. Go ahead and plug everything in. So, P1, 162.1 kPa. My V1, 30 liters. T1, 312 K equals 2. My new pressure, 101.325 kPa. Don't know my new volume. And I have 273 K. for my new temperature. So 5 numbers, 1 variable still to be found. Okay, how do I solve something like this? Well, since this is a fraction, to get rid of fractions, I need to multiply by the reciprocal. And I have to do it to both sides. So over here on this side, the 273s get canceled, the 101s get canceled. The only thing that's going to be left on that side is the V2. Over here, the kelvins will be canceled, the kPAs will be canceled, and the only unit left will be liters, the L for liters. Now, this is all multiply and divide, so it does not matter which one you do first. So 273 times the 162.1 times the 30, divide by the 101.325, divide by the 312, and I end up with my V2 equal to basically 42 liters. Came out 41.995. I can round that to 42 liters. So there was my first answer, 42 liters. So that's what it takes to solve a combined gas law problem. Put all 5 in, solve for the one that's missing. Any questions on that? All right, problem 2. Basically going to do the same thing, but this time they did give me all 5 numbers, so make it a little bit easier. Here is my first pressure, 150 kPa, 27 degrees Celsius, so I'm going to have to make that into Kelvin. First volume, 4 liters. New pressure, 600 kPa. New temperature, 127 degrees Celsius. Find the new volume. So pretty much like problem 1, but I can see all 5 numbers. And again, just like before, 27 degrees plus 273. That's 300 K. So that'll be my T1. My T2 will be 127 degrees plus 273. And that ends up being 400 K. Write my equation down. Plug everybody in. So let's see, 150 kPa and 4 liters over 300 K. And that's going to equal 600 kPa, new V2 over 400 K. Again, I want the V2 all by itself, so on both sides, multiply by the reciprocal of what's by the V2. 400 K over 600 kPa over there. 400 K over 600 kPa on this side. K's get canceled, kPa's get canceled, leave me just in liters. Over here, these things get canceled. So I'm just going to have my V2. And when I get all said and done, basically 1.333 liters is going to be my V2, which, by the way, that's 4/3 liters. So V2 equaled 1.333 liters. Normal problem, 5 numbers, plug in the 5 numbers, solve for the one that's missing. STP problem, you only see 3 numbers, but there's really still 5 numbers there. Temperatures have to be in Kelvin. Use the reciprocal to solve for it. Okay, problem 3. Doesn't matter, I can solve for volume, I can solve for pressure. Basically going to do the same thing. Here's my volume, pressure, doesn't matter what units I'm in as long as they're the same. Here's my first temperature, have to change that to Kelvin. New temperature, new volume, find the new pressure. So, P1 V1 over T1, P2 V2 over T2. Let's start putting things in. We've got first pressure, 760 millimeters mercury. First volume, 15 liters. Temperature, okay, add 273 here. That ends up being 240 K. So over here we have 240 K. Okay, now the other one. Well, I don't know the new pressure. P2, new volume, 25 liters. And new temperature, well, 87 degrees plus 273 is 360 K. So 360 K goes here. That's our T2. Again, multiply both sides by the reciprocal to get the P2 all by itself. So we're going to have 360 K over 25 liters on both sides. And when we go ahead and multiply everything out and divide, 360 times the 760 times the 15, divide by the 25, divide by the 240, we end up with P2 equals 684 millimeters of mercury. So in that case, I solved for P2. Any questions? All right. How about solving for temperature? So we want to know a new Celsius temperature. It was at STP. Okay. So remember that the 240 milliliters, it says it's STP, so that means it's at 0 degrees Celsius and 1 atmosphere. Okay? And then it goes to a new pressure, 1.48 atmospheres, and a new volume of 180 milliliters. So P1 V1 over T1, P2 V2 over T2. Let's start plugging in everything. First pressure was 1 atmosphere. First volume, 240 milliliters. No problem that it's in milliliters as long as they're both in milliliters. First temperature, 0 degrees Celsius, 273 K. Remember, we have to always add 273. We can't divide by 0 anyway. Equals, okay, 1.48 atmospheres, 180 milliliters, and over T2. Now, just like in those previous examples, when we have something on the bottom, that's not just multiplier divide, okay? I need to do cross multiply. Okay? So that'll look like, basically, I'll have my 1 atmosphere, my 240 milliliters, and then T2 equal to my 1.48 atmospheres, 180 milliliters, and then 273 K. And then now that I have the cross multiplied part, all I got to do is now divide both sides by the 1 ATM. Of course, dividing by 1 is not going to do anything. And the 240. Do it on this side. Do it over here. The 1 atmosphere and the 240 milliliters. So essentially, I've got 1.48 times 180 times the 273 divided by the 240 divided by 1. So when you do all of that, we're going to end up with a T2 that's equal to 303 K. But they don't want to know the temperature in Kelvin. They want the temperature in Celsius. So I still have to subtract 273 to put it back into Celsius. So my final answer ends up being 30 degrees Celsius. So notice how every single one of these, I'm tending to do them the same way. Write down your equation, plug in all the numbers. Sometimes I can simply multiply or divide. Sometimes I need to do the cross multiply, then do a divide so that the one unknown is all by itself. And you got to make sure and read the problem. Did they want an answer in Kelvin? Did they want an answer in Celsius? If I started out in Celsius, I want to end up in Celsius. If it says tell me in Kelvin, then I would leave it in Kelvin. So it kind of depends for that last part. Any questions on that one? Had to do a little bit more. All right, last one here. No numbers. So just like in previous ones, we're going to make some things up. We do want to kind of keep things as simple as we can. So we have a volume. How would the volume change if the temperature of the air inside is doubled while the pressure is reduced to half of what it was? Now, they didn't tell me any restrictions, so you know what? I'm just going to do the temperature in Kelvin. Makes it easier. I don't have to change it first. And all it says is the pressure has to be reduced. So let's put some numbers in. All right, T1. Okay, we're already in Kelvin. We want to double. So let's say we start at 300 K, and then T2, we'll double it to 600 K. In Kelvin, just double it. Okay, we already know that if we're in Celsius, it doesn't quite work right with the doubling, so let's just leave it in Kelvin. What about pressure? All right, hey, let's make it easy. The pressure, let's say it was 2 atmospheres, and then we reduced it to half. So now let's make the second one 1 atmosphere. That's always easier because times 1 divided by 1, it's not going to change things much. All right, what we really want to know is what's going to happen to the volume. So let's start off with, say, the volume was 10 liters. Okay, 10's a nice round number. Now I have my 5 numbers. And honestly, folks, it's not going to matter as long as whatever that one was, I doubled, and whatever this one was, I cut in half, and then let's look at some round number for my volume. So, just like we had P1 V1 over T1, P2 V2 over T2. Let's go ahead and plug in all our things. So, P1, 2 atmospheres. V1, 10 liters. Over 300 K. Now we're going to go to P2, 1 atmosphere. We don't know the new volume. That's what we want to see how it changes. And my new temperature, 600 K. I want to find the new volume. So basically 600 K over 1 atmosphere, so that this side will get all canceled out. But if I do that to one side, I have to do it to the other side. 600 K over my 1 atmosphere. And the reason I picked these numbers, note what happened. The 1 atmosphere, well, that got canceled with the atmosphere, left me a 2. 600 K over 300 K leaves me a 2. 2 times 2 times the 10 is, my V2 is 40 liters. So it was at 10, it went to 40. Basically, how did it change? Times 4 is how the change went. Or we call that quadrupled. So if the temperature got doubled and the pressure got cut in half, my volume got quadrupled. That's how so it's a little bit more complicated when it's the combined gas law. Now, last thing I want to go over for combined. Really, when you think about it, the other 3 laws are all here, because the other 3 laws all had a particular condition. For example, start with the combined gas law and go constant temperature. Okay? Constant temperature means T1 equals T2, which cancel those out, and I now have Boyle's law. P1 V1 equals P2 V2. If instead I said, hey, let's make it constant pressure. Well, constant pressure means P1 equals P2. And in that case then, the pressures cancel out, and I am left with Charles' law. So the combined gas law actually has the other 3 laws in it. Every time I say this doesn't change or this is constant, I throw out that letter. So constant temperature, I threw out the T's, I'm left with Boyle's law. Constant pressure, throw out the P's, and I'm left with Charles' law. Constant volume, throw out the V's, and I'm left with Guy-Lussac's law. Okay, any questions? Okay.